and the Science Foundation in China. And he was awarded also in 2009 with the Symmetry Journal Young Investigator Award. And he joined our institute 2 years ago with a Juan de la Silva Formation Grant. And I think, if I'm not wrong, that he will reincorporate soon with an incorporation grant. So we can see him here soon. Today he will talk about his research on cosmology and applying modern techniques. The talk is entitled Cosmology, Ensuing from Machine Learning. So please, Martiros, the floor is yours.
Okay, thank you very much. Welcome, everyone. This was a nice introduction. Thanks for this. So let me just start the sharing of my screen. And go to slideshow. Okay, well, so yeah, today I'm going to talk a little bit about cosmology and about machine learning. So in this time, I would like to discuss the situation based on our results when we use machine learning and what we learn about cosmology. And I have some sort of agenda for today's talk. So I would like to discuss two particular two machine learning algorithms. One is the Gaussian process. And in this scenario, I would like to discuss the FT gravity reconstruction directly from the data. So to this, we will come soon and I will explain how it is working. The second approach that I'm using in my research is Bayesian machine learning. With this framework, I would like to discuss with you about deviation from the cold dark matter paradigm that we observed, we learned recently, and which is connected to the Hubble zero tension problem. Before discussing the results, I would like to start my presentation, my talk, discussing a little bit about cosmology. This is something that we know, so therefore this would be really very brief review. So then I would like to discuss a little bit about machine learning, asking what machine learning is, because nowadays there is some sort of confusion in the community. Everyone is thinking that the machine learning is doing something magic, and it's very hard to understand, it's very hard to implement, etc. So the goal of this point of discussion is to develop an intuition of a physicist how to understand machine learning. So if I succeed with all of those steps, I will arrive to conclusion, and that's all. Yeah. So let me just start. So we and universe. So what we have actually and what we are doing actually. So we have a bunch of data and we want to explain this data. Yeah, we have actually two possibilities for this moment. One is general relativity, which is here, and the other one is the modification of gravity. So it's no matter actually from which directions, from which point you are starting to work. So when you want to explain observational data, you are coming up to this picture. Yeah, which is saying that more or less the energy budget of the universe should be divided between dark energy, between dark matter, and between something that we observe. And different estimations already exist. We are very familiar with them. We know how to work with them thanks to data and thanks to theory. What we know is that dark energy should be about 70%, dark matter should be about 30%, and the rest, what we observe, what we see in terms of the stars, galaxies, or whatever is about 5%. So of course, these numbers are changing, and there could be two reasons. One is could be related to the technological improvement of the experiments and etc. And the second option, the second possibility that the numbers are changing is about physics. So we are not certain about physics, we are not certain about other stuff. So therefore we continue and we are collecting data and we are trying to understand what is going on. What I'm doing dark energy physics, more or less. I'm trying to develop models. So we have, of course, here you see that we have a bunch of models. And I'm working with some of them, and I'm trying also to develop another model. And the idea is to unify dark energy and dark matter. From the old research, we know that chip ligand gas, for instance, that I have mentioned here, it's interesting because it allows to unify dark energy and dark matter. But the point is that dark energy and dark matter operates on different scales. They have different properties. Yeah, and then they do different job. For instance, dark energy is working against gravity to give the accelerated expansion of the universe. But dark matter does something else. It's responsible for the structure formation. Therefore, it is a little bit hard to understand how those two components operating on different scales, having different properties, can be unified. Yeah, this is interesting problem. I'm going for this moment. I'm working in this direction, trying to find an alternative approach for unifying dark energy and dark matter. Recently, we came up to the idea that the unification could be done thanks to the acceleration parameter. And in this way, we started to build completely new models of dark energy. But this is, let's say, in a progress. This information was just some sort of information completing the introductory part started by Juan Carlos. Probably this is what we know and what I can discuss with you guys, because you know this very well. Therefore, let me just jump to the second topic that I would like to discuss. And as I mentioned, this is about machine learning. And what I would like to ask is this: what machine learning is, how we understand it, and how we can use it. So nowadays, especially when I'm discussing about machine learning with some guys, I see that there is some sort of misunderstanding of the situation. First of all, this is related to the deep nets. And when I'm discussing to starting a project and etc., some guys are saying, but machine learning is just deep learning. But this is not true, actually. And this cartoon that I have here is the most simplest. Yeah, there are many other complicated definitions of what artificial intelligence is, what machine learning is, what deep learning is. But I'm trying to keep the stuff to be not too much complicated, allowing us to develop an intuition. In this regard, you see that deep learning is just a part of machine learning. There are many other machine learning. So, and as I mentioned today, we will discuss two of them, Gaussian process and Bayesian machine learning. And if we are asking what machine learning is, probably this is the most interesting definition of the machine learning useful for physicists. It says just, if you are able to calculate probabilities, believe that you are doing machine learning. So, and actually it is something like that. So how we are making our machines to learn to do something. So we are doing this by helping machines to understand the environment in terms of probabilities. And both of them, machine learning and its sub-components, allows us to do this artificial intelligence stuff. So let me just give an example to understand what is going on and what actually deep learning is doing, neural nets are doing, because nowadays there is a lot of discussion about physics and about deep nets, where the persons are using, they are crafting different models, and they are using this in physics, especially in astrophysics, in cosmology, and etc. And they are getting very fantastic results. And what is the beyond? Yeah, about this deep learning. So let me just give an example. This is also a simplified version. So how in general we should understand the machine learning. So in the cartoon and the up part of this cartoon, so this is a simple classifier So you have input, which is car. So then you have a person who is just labeling and trying to understand what are symmetries, what are the characteristics of this object. And then you are this image, this input is passing through the network, and then it's giving an output saying that this is car or this is not car. Now, why we are interested in deep learning? Deep learning says, okay, let us remove this guy from here. So, and make the end-to-end system, which will take input, will figure out the features of this input, and then will give us the result. So in this case, it would be able to distinguish this is car, or this is cat, or this is the dog, or what is it. But the situation is not such simple because there is a bias. For instance, that this bias could be in data. So therefore, nowadays in many research, you see that this guy is coming back, because having this guy back, you have a possibility to speed up the feature extraction part of the data, which speed up the training. Speed up the training and speed up the decision making or making processes or other processes. Imagine that you have a situation when you are working on healthcare problems, so you build a system, and the learning process with the data took 2 months. And after 2 months, it would appear that what you invested, what you did, was useless, because someone else, including just a person, one person or group of persons, were able to speed up the learning process. In this regard, that the worry that at some point, this machine learning will make a lot of persons to be jobless is not true, because we still are not able to understand what is going on in machine learning and how everything is working. So if you remember, I mentioned that machine learning is just working with probabilities and learning how to calculate the probabilities in order to do something, and different structures and different machine learning algorithms suppose a way to calculate these probabilities. And deep learning says, like, approximate the calculation of the probabilities in terms, for instance, polynomials. Of course, you add their you add their non-linearities. You do different cool stuff, applying softmax, for instance, to figure out the probabilities, and etc. and etc. But what we should keep in mind that each of machine learning algorithm, despite of this discussion, also allows us to approximate the probabilities, allows us to simplify the calculations of the probabilities based on which our system is able to do something. But besides the problems, besides the main problem that I mentioned about bias, there is another problem, especially with DeepNet. So the one problem that I would like to mention is that for doing the learning, we need a lot of data. If we have less data, or we are not careful with our data, so we can get very strange results. And since mostly the computations of the probabilities are very complex, we are operating with black box, and eventually we are not able to interpret, to explain the others how this or that result we got. But this is not something that we should give up. Of course, there are many other options, techniques, whatever the persons are inventing in order to overcome different problems. And this is helping us also in physics. I already have mentioned that machine learning helps for better understanding physics, but at the same time, physics helps to provide the data to do machine learning. So there is some sort of cycle that physics goes to machine learning and machine learning goes to physics. And recently there appear so-called physics-informed machine learning, or physics-informed deep learning. Where not only you use not only the data, but you use some constraints or some symmetries or whatever from physics, which allows you to speed up the process and allows very precisely model different complex systems, including hydrodynamics, including astrophysics, and etc. So the field is huge. The progress there is very fast. And since I'm using machine learning as a tool in cosmology, let me just finish the discussion, the overview, and just keep from this the fact that machine learning is based on the calculations of the probabilities, and who does in his life probability calculation. So this person is doing machine learning. Now it's already time, I guess, to discuss a very specific process, very specific machine learning algorithm, which is known as Gaussian processes. And I would like to develop some sort of intuition how it is working, and at the same time to demonstrate how we can use this in cosmology and what are the tasks that actually we can do, and at the same time to discuss what are the limitations that we impose on the problem that we use when we use Gaussian processes. So this is just first two lines, first two paragraphs. Those are just the classical definitions of Gaussian. One is a Gaussian distribution for the random variable, the other one for the function. So what we need just the second paragraph in order to understand what Gaussian process is. Gaussian process is the approximation of the function, but this is not just the approximation. So we learn this approximation from the data. So what we actually do, we took some Gaussian prior, then we put some data, and based on this data, we update our belief. And then we are adding another data, we update our belief, and when I'm saying we update our belief, means that we are changing the shape of the Gaussian prior that we put in advance. And eventually we are coming to the situation that based on the data, we updated our belief, and from this one, so we figure out what is the parametric form, or what is the form of the function which can represent this data. The key guy in this process is the covariance function. So I have one of them, which is saying how 2 points in this function should be correlated. You see, in this case, if the points are too far, so the correlation is very weak. So if the points are closer to each other, the correlation is strong. And on the other hand, you see that any covariant function has hyperparameters, and the first task that we want to use Gaussian process is to learn these hyperparameters. There is an option, and for instance, it is perfectly implemented in GAPP. So this is Python-based open source code. So what this code does, it allows us to learn the hyperparameters based on data. So before going to an example and to discussion about the results, let me tell a little bit about the problems. For instance, you see that this covariance or kernel function is smooth function. So which means that provided the data, eventually we will reconstruct the smooth function, smooth behavior of the function from this data. So this means that, for instance, if we want to study some singularities, even if we know that there is singularity in the model, so we are not able to do this because the smooth, the mean and the errors or whatever that we reconstructed using Gaussian process is smooth. So this is one of the problems. The other one, as you probably got already, it's a fully probabilistic framework, which means that when you finish the reconstruction, you should pay attention not only to the mean, but also to the errors. And if the errors are too big, so practically you are not able to make some inference, to say, to give even a hint. So therefore, if you want to make this process to work for your model, for your task, you should be careful about the errors. And when the errors are good enough, So only in that case you can say something about your problem. Okay, so just to go to the problem, let me just describe the data which we have in this table. So this is the expansion rate data. 30 points are coming from the cosmic chronometers, and the other 10 points are coming from the BAO. So cosmologists are using, I mean, we are using this data. We are not asking about these extractions and etc. The only thing that we should keep in mind is that these 30 points, which are at upper part of the table, so those are model-independent reconstructions or extractions of the expansion rate data, while in the BAO case, in the bottom, in case of the data here, so this is the extraction of the data is based on the lambda CDM. So we take a model, and based on the model, we are doing the extraction. Now, let me just discuss how we can use, for instance, the expansion rate data, how we can use Gaussian process in cosmology to do some fantastic stuff. But before, let me just describe you the result when we have expansion rate data is in table in the previous slide, and we apply Gaussian processes, and what we get. Yeah, so we get the extraction of the, we reconstructed the expansion rate, we extracted also 1 sigma error of the process. So then following some mathematics, we are able also to reconstruct higher order derivatives of this guy and reconstruct the errors. Now you see here, and these red dots and these errors they are representing our data. And you see here that not only the mean has a reasonable behavior, for instance, from here it's more easy, it is easier to see here. So not only the mean is smooth and has been reconstructed very well. Yeah, so we also good with the errors. Yeah, errors looks nice. Yeah, so then let's see if we have this picture, what we can say about, for instance, FT cosmology, which is known as torsional gravity, let's say. So what it says, okay, let us not only consider T torsion, but also consider some arbitrary function of T. Yeah, so, and when you take Friedman-Robertson-Walker matrix, so you are coming up to such equations. And also it is known that the torsion scalar for the Friedman-Robertson-Walker matrix is just -6 Hubble square. Yeah, so which means that since we are already applying Gaussian process, we reconstructed the expansion rate, so we are free to provide model-independent reconstruction of the torsion thanks to this guy. So this is very important. Probably I need to stress that Gaussian process directly works with big data and allows us to learn and allows us to do model-independent analysis. This is very important, and for instance, this can be used in studies of interacting dark energy models where you don't assume any form of the interaction, and thanks to the reconstruction, for instance, of the expansion rate data, so you are able to reconstruct the form of this interaction guy, yeah, without assuming any parametrization. So therefore, usually when you have some paper or whatever, when they are using Gaussian process, they are saying we are doing model-independent reconstruction, or we are doing model-independent analysis of the data, because only what the model we use, it's a kernel to learn the data, and nothing else. It is not related to, we are not using some sort of physics, some sort of model which is coming from the physics. We are not doing a fit, and from there we fix free parameters. We are not doing this. We are directly working with data. So now let me come back to FT. So we know that if we introduce the energy density of dark energy in this way. If we introduce pressure of dark energy in this way, so we have dark energy equation of state parameter of which reads in this way. So these equations, so we can write in this way. Yeah, we are coming to lambda CDM, yeah, in some sense. Now the question is how we can, if we go, let me just come back to this slide. So if we go by using classical tools, what do we need to do in order to analyze, for instance, this problem? Yeah, we assume a form of f. Then we calculate ft, which is derivative. So then we put all together, and then if we are lucky, we do analytical calculations, or not, we do numerical integration or whatever, and then we put this and compare with the observational data to feed the values of the free parameters representing this f. So now we don't want to this. We want to do, we are suggesting to do the following. We are saying, okay, start from this equation, take into account that t is minus 6 Hubble square. This is derivative, which is written here, and taking into account that the derivative can be represented in this way. Now, if I take delta z very small, so I am able to do, to have a well approximation of the derivative, which is sitting here. And then starting from here, taking into account all these steps, I am coming up to the equation which is allowing us to reconstruct the form of ft. Of course, in this writing, you see that we are reconstructing fz, f function from redshift, but we have also that t is minus 6 Hubble square, which is function of redshift 2. So we can eliminate redshift from both sides, from both parts, and eventually we can come up to ft. And what we obtain here, we obtain a new parametrization, a new form of ft gravity based on the mean of the reconstruction from the Gaussian processes. And this is one parametrization of ft gravity, where this minus 2 lambda has this form, which is coming from dark matter. By the way, I would like to mention that Gaussian processes can be used also to constrain different models, different cosmological models, including modified theories gravity, including different forms of dark energy models that I have on the first slide of my presentation. Now, this was the result that we got in 2020. So we continue in the working in this direction. But at the same time, we got interested by Bayesian machine learning. The idea is nice. I mean, the idea which is behind the Bayesian machine learning is very nice, is very interesting, and seems it can provide many results, many good results and different results. And today I'm going to discuss with you about one of the results that we have for this moment. But before arriving to this point, let me just describe what Bayesian machine learning is. And for this reason, I would like to start with Bayes theorem, which is saying that the posterior, which means what is the model that can, what is the probability, or what is my belief that given model can explain the data. And this posterior can be represented in terms of the priors that we impose on the model based on the evidence which is coming from the data. And here we have a likelihood which says that given model can explain the data. Our belief that the given model can explain the data. Now, if you have such scenario, how you can turn, the question is how you can turn this to a machine learning problem. And there is one, there is only one, let's say, approach, which is saying that instead of this sign equality, consider the optimization problem. In all machine learnings, what we are doing, so we are considering the optimization problem, which means that take something and compare to your belief and decide what you take as an approximation, how much it is close to your belief. Now, let us do this here and get Bayesian machine learning. Now, what we want, so we want not to calculate this all because they are in general some sort of some complicated, I mean, to do calculations here, you need to calculate complicated integrals or summation, do summations, depends on the type of your variable. And we say, okay, we don't need to do the calculations. Let's invent or let's take some distributions and check. So this distribution close to our posterior, to our belief that the model can explain given data or not. Yeah, and here directly you see that we have very nice possibility. And this is based on this part, prior and likelihood. But here we are not looking to the likelihood as an object to calculate, but we are saying, okay, so we have a model, let's generate the data. Because in that point, we are certain, or we believe that the model can explain the data. And based on this one, let's generate bases or generate some families of distributions and compare. Those are close to our prior or not. So in this way, we have optimization problem and we have a machine learning process. So this is what I have written here, that if we want to use Bayesian machine learning, we need to define physics. We need to understand the model in order eventually, at the end of the day, to understand what we got is something reasonable or not. Yeah, and based on the generated data, which is based on our model, which is here, let's update our belief, let's update our prior, as has been done in case of Gaussian process. So we put Gaussian prior, then started to inject data, and based on this data, we started to update the prior, and eventually we get a shape. Yeah, we updated the prior, and we got some nice shape, not some nice shape. Not something like you know, so two parallel lines in nowhere. Yeah, so if we understood this, if we accept this, of course, what I discussed, this is just to develop an intuition, because you know there are many possibilities, there are many tools how to obtain, how to generate, and etc. In our analysis, we are using PyMC. So this is nice tool, have all possibilities, I mean, for all tools for this moment and necessary for our analysis. But of course, there are other options, other tools. I personally didn't have time to study them, to understand which one is better. I just have one which is working and which is working well, and it is easy to integrate to the previous codes that we developed. So for this moment, we are keeping working on this, but eventually one day we need to make a comparison to see which one is working faster, to estimate the precisions, and etc. Now let me just finalize here. In general, why we want to do machine learning. So we want to do machine learning instead of doing simple fit. When we have learned, we can do predictions and extend the result to the unseen regimes. So in particular, when there is no data yet. This can be helpful for designing new experiments and observations. The real data, so this is very important. So the real data can be used at the end to validate learned results. So this is very important. So and we are following mainly this logic. Yeah, we have the model, we generate the data, we learn, and then we use real data in order to see, to validate what we learn is reasonable or not. Now what we did is about the Hubble zero tangent problem. But first of all, we started to ask, so why interacting dark energy models work? The dark energy models are working good, I mean, they are doing good compared to non-interacting dark energy models. And before coming to this question again, let me remind you how we nowadays, how we understand how to introduce interacting dark energy models. So, and it is done thanks to those two equations where Q is the interaction term. Of course, we don't know how and from where this is coming. So what we know that we have a data, and when we are following this system of equations with some parameterizations of Q, so then data says that the parameters, free parameters used in the form of Q are not zero. Yeah, which means that the data gives a hint that there could be an interaction. And when we are going to, and we are analyzing the results, including the Hubble zero tension problem, we see that these interactions plays a lot of important role and can allow us in practice to solve this tension problem, for instance. And also it can help to solve sigma 8 tension problem. It allows us to avoid singularities and etc. But the question is from where this is coming. So is there a way to understand from where it is coming? And having this question in our mind, we just realize that what is happening, which is known also, and this is like a simple algebra, simple mathematics, that if you take Q from the right-hand side to the left-hand side, you introduce some sort of effective fluid, effective dark energy here and effective dark matter here. Even if you consider the model of cold, if you consider cold dark matter model, where this guy is just zero, when you take Q here, you introduce non-cold dark matter, effective non-cold dark matter. Now the task was to understand what machine learning says us. This is going to be exactly zero or not. If it is not, when those guys are zero, then this can be an explanation why we took this zero and here not zero, works well. And what we did, we took the model, yeah, where besides the equation of state of dark energy, we have also dark matter. Yeah, this is not zero. So we want to fit, this is free parameter, we want to fit to see it's zero or not. I mean, we want to learn, yeah, because I'm talking about Bayesian machine learning, we want to learn this is zero or not. So more results, is it possible to find in this paper, in this paper, which has been done with Emily and Gluja from Poland. Now, what we observe, so we consider it two sub problems. One, we say, in one case, we say, okay, let's dark matter equation, this parameter to be free and to be fitted, to be learned. But dark energy is the cosmological constant, which means that omega dark energy is -1. So we are coming to this equation. So, and now using this, we started our data generation process, generating process, and learning process. And we came up to these results. And what you see here, it is here, the main result saying that cold dark energy, cold dark matter, sorry, is not cold, yeah, because the omega dark matter is not zero. It's even not such number that we can approximate it to be zero. But on the other hand, we saw very interesting situation that Hubble zero tension problem cannot be solved. Now, what means Hubble zero tension problem? So we know that from the Planck's CMB data, when the lambda CDM has been used, the value of the Hubble zero parameter, the value of the Hubble zero parameter has been obtained to be this 67.4 plus minus 0.5 with the proper unit. So, but on the other hand, when you look to the Hubble Space Telescope, the Hubble zero, the guys got 73 and 52 plus minus 1, 62. Yeah, and you see that there is a huge difference. Yeah, once again, yeah, you have the model, you have the data, you have the value reduction, and you get this. You have model independent reduction of the value, extraction of the value of the same parameter, and you have something this. And this is a tension. Now there are two questions. I am mentioning about two, and I will explain why. One, this could be about physics, about lambda CDM. On the other hand, there could be a possibility that we have a problem with observations, you know, scales, etc., etc., etc. But also there could be a third possibility, which is more complicated, where we have a mix of those, that we have a problem with physics and we have a problem with observations. But this is too much complicated to answer now. And we eventually want to do step by step. We want to figure out there is a problem with physics or not, and to get some certainty in this part with some probabilities or with some belief. When we establish this, we go to the other step. So when we figure out that with this probability, there is no problem with the observations, then already with both of them, we can try to explore the third option. Now you see that there is, let me just come back again to this result, that when dark energy is the cosmological constant, so we see that the cold dark matter is not cold. Yeah, we have deviation from this guy to be zero, and we are not able to solve Hubble zero tension problem. But this is the end of the story, or we have other option too. So we have other option too, but before going to this, let me just demonstrate what we learned. So this is the behavior of the accelerated. Okay, let me start from here. So this is the expansion rate data, so which has been learned. And then at the end, as you remember, I said that we are following the logic in this way. So we do the learning, and at the end, we are using the data to check, to validate what we learn, or what we learn is correct or not. And you see that our learning is nice, and you also should notice that, let me just come back here, that we consider it three redshift ranges. Yeah, first it's redshift 0.2, 0.2.5. So in both cases, we have expansion rate data and we can validate the results. But the existing expansion rate data covers just half of this range. Yes, the rest started from 2.5 to 5 is just forecasting. Yeah, so this is also very important to learn that Bayesian machine learning, since it is based on the data generation process, it allows us to do a forecast and go to the regimes where the expansion rate or there is no data. Yeah, and this is the case of the expansion rate data. And you see that the learning was quite successful. And you see that here we have the accelerated expansion, we have transition to it, and etc. So here also I would like to mention that since you are able to reconstruct the expansion rate data and the first order derivative of it from the Gaussian process allows you to do model independent reconstruction of the acceleration parameter, showing that this accelerated expansion is not data or is not model dependent process. So it is supported by data. Now we did the other analysis also. We said, okay, that probably the problem was in the previous case that we couldn't solve the expansion, the Hubble zero tension problem, probably was in the fact that we said, okay, dark energy is the cosmological constant and we fix this parameter. Now let us consider more general case that this is free parameter, this is free parameter, and those are free parameters. Yeah, so and then start to fit, and then start to learn. So we are not able to use fit terminology here. We should say learn, because we are doing Bayesian machine learning. We are doing machine learning. So, and again, we consider it for three different redshift ranges. And in each case, we saw that the Hubble zero tangent problem can be solved if you are not forcing dark energy to be exactly the cosmological constant. And in all cases, we observe the deviation from the cold dark matter, because these guys, as in the previous case, is not exactly zero, or it is not something which is close to zero that we can say, okay, let's close our eyes and just accept that this is zero. And on the other hand, the constraints, when this omega dark energy was a free parameter, we obtain something which is very close to the real observations. I mean, close to the result that have been obtained previously. Now, let me just give a conclusion, mini conclusion of the situation related to associated to the results that we have, and it could be in this form. We learned that on cosmological scales there is a deviation from the cold dark matter paradigm. The Hubble zero tangent problem can be solved without interacting dark energy models, but just deviating from the cold dark matter. This explains why interacting dark energy models work in general. We see the constraints on dark energy are consistent with known results. Eventually, we learn that understanding both dark energy and dark matter is very important to solve the Hubble zero tangent problem. We need to be very careful about this point. And also here, I would like to demonstrate the learned results when we started to compare with the models. In this case, which is corresponding to redshift 0 to 5. So we have some sort of tension with high redshift data. But if we take 1 sigma errors, learned 1 sigma errors on the parameters, this deviation disappears. Yeah, this is some sort of hint also what is upper or what is below, what is upper or below bounds on this omega dark matter deviation. So for this, we still need to do something. And this is not this is just the initial result. So we need to do more, taking other observables and etc. to figure out what is going on. Eventually, let me just come back to the conclusion and do this in this way. Yeah, machine learning is a set of algorithms cooperating together in a very clever way. Gaussian process is one of the machine learning algorithms working directly with data. It reconstructs the possible form of the function representing data. No anymore you need to use any parameterization to represent your data. And this allows you to do different model-independent analysis, constrain the models, and etc. As I already mentioned, it is useful for dark energy study, for constraining cosmological models, and also for the reconstruction of modified theories of gravity, in case here I have discussed, it's FT. Even more, it appears very useful for the Swain-Planck criteria study. So when you use Gaussian process, you don't need to know the form of the potential, and you don't need to have any dark energy model to constrain the potential, and with this one go to study Swain-Planck criteria. So with Gaussian process, directly you go to the Swain-Planck criteria. On the other hand, today I was discussing a little bit about Bayesian machine learning, which is another machine learning algorithm based on data generation. So we started from Bayes theorem, and we just said, okay, not calculate, but compare and the optimization problem, choose something and compare with something to see the deviation, how much. And if the deviation is small, then you say, okay, what the approximation I'm trying to use is the good one. Then generate the other one and compare, and to decide this is going to be far or this is going to be a new one, and update your belief based on this one. And in this, and in this case, so we observed deviation from the cold dark matter paradigm, so which explains why in general we can have interacting dark energy models and why they are working. And actually, it motivates us to do three more works. For instance, here we applied this Bayesian machine learning and to swim plant criteria to constrain the cosmological models. And here we use the cosmic opacity directly to constrain the cosmological models. And here we were able to learn using Bayesian machine learning single viscous dark universe models able to solve Hubble zero tension problem, which previously has not been possible. I mean, previously the persons tried usual models of viscous fluid and they couldn't solve the Hubble zero tension problem. But let's say with machine learning, we learn a new form and we demonstrated that we are solving with this the Hubble zero tension problem, and of course observing deviation from the cold dark matter initiated a huge search in data to see is it possible from the data from the other data sets to see the deviation. This is real or this is something coming from the machine learning algorithm. So in other words, in order to understand, should we believe on this or not? And one of the initial results with Gaussian processes shows, and I hope that very soon it would be on archive, it shows that we have a place to believe that there is deviation from the cold dark matter paradigm. So thank you very much for your attention. And if there are some questions, comments, or suggestions, so please, we can communicate. We can just exchange emails to see how the things are going. Thank you.
Thank you, Martiros, for this nice talk about the possibilities of learning with machine learning. We have time for some questions. So please, if you have some question, just unmute yourself or raise your hand. Yes, go ahead, please.
Hi, Martiros. So thank you very much for nice presentation. So as I understand, your interacting dark energy models explains the current observations between Hubble telescope and versus Planck, but does it make some prediction? Because if the value of H0 from the local observations were a bit different, your model still applies to that, or does it have some range that applies only this data that we currently observe? Because there is also other observations like TRGB or other methods, which they don't quite agree in the local observations of Hubble constant. So your model is specific to this, or can it accommodate other values of H0?
Okay, well, the result that we have is based on the expansion rate data, which has been generated from the model. So I didn't check, for instance, what is going on and what I can say about the Hubble zero tension problem if I use luminosity. Yeah, where I integrate from 1 over my model, then I integrate, then I get the luminosity, and from this I generate the data and do the learning. Yeah, probably in this case, when I'm going in this way, what you are saying is correct. I didn't check this, but if I am taking the expansion rate data and I'm doing the learning generated on the data, which is based on my model, so I'm getting the picture that I have deviation from the cold dark matter. But okay, so probably let me go here again and to say that in our model, I don't have interacting dark energy models. I don't have, because you see, if I have interaction, if I would have interaction, then I should have some extra parameter or degree of freedom, which should appear in these equations, but I don't have. So those are the solutions from those equations where Q is equal 0. I don't have interacting. I'm getting at the end, I'm getting that there is deviation from the cold dark matter. So here is 0, here is 0, and this is not 0. And compared to the case that when this is 0, and those are not zeros. When I'm taking these guys here I'm getting something effective, which is not cold anymore. So I'm confirming this. I don't have a interacting. So this is interacting dark energy models here. This is very important to note. If I'm taking this guy to be the guy that I'm generating from this model, then I see that I have deviation from the cold dark matter, deviation from cold dark matter. When I'm not fixing this to be exactly cosmological constant, but this is free and I'm learning, then I see that for Hubble zero, I am getting these results. Now my point is that if I will take, like, from my model, I will generate large-scale structure formation or whatever, probably from there I will see that there is no deviation, or there is deviation, but still this is not close to the Planck. And still the Hubble zero tangent problem exists and it is not solved. So what I can say here, I can say that we found, we learned a hint that deviation from the cold dark matter, when we properly treat the dark energy, so we are able to solve the Hubble zero tangent problem.
Okay, many thanks.
Okay, thanks.
Is there any other quick question? If not, I have one basic question myself, and is when you explain about the Gaussian process and you explain the meaning, you introduced that there are a couple of hyperparameters. Do they have some physical meaning in your model, or they are just?
No, of course. I mean, physical meaning. No. I mean, let us just. Okay, so those are the parameters, hyperparameters, allowing you to get the shape of the curves.
Mm-hmm. But can they be so do they correspond to some physics, these parameters?
No. I mean, okay. No. They just, yeah, okay. No, they just okay, they just say you, okay, among other things, they say you how two points are correlated.
Correlated, that's it. Okay.
Of course, okay, so what you are asking, your question has a sense, yeah, makes sense. Because eventually, based on these ones, you get some sort of reconstruction, and then you are using this in your model. So, and then this can affect. But the point is that we have many different kernels. We did many different tests. Yeah, we kernels with 3 parameters, kernels with 100 parameters or whatever. After the learning, especially on the expansion rate data, after learning, we saw that what we obtained, they are reasonably close to each other. Yeah, because for instance, if the point is that, for instance, we reconstructed and we got this form for FT. So this is model independent reconstruction form of FT. So if you will use other kernels, again, you will come up to this.
Okay, I got your point. Okay.
Yeah, depends on the, I mean, of course, the values of this, for instance, this free parameter could be different, but this is, let's say, within 2%. So far, we observed using different kernels that have been used for, I don't know, 10 years, yeah, in the community. The difference is just within 2%. So in this case, I mean, everything depends on the data. The data is very important stuff nowadays.
Okay, thank you.
Yeah, if you have some biased data, so everything will be blown up. Classifiers, I don't know, recommendation systems, and etc. Most likely they will blow up, and some of them even can be hacked. Yeah, so this is the issue.
Thank you so much.
Welcome.
Any other quick question? If not, maybe we can stop here. Thank you very much, Martiros, again.
Thank you.
And see you all in the next pizza seminar.
Yeah, see you.
Bye.
Bye. Adeo.